Now, Euclid's Elements was the most influential mathematics book of all time, and it developed and codified what came to be known as Euclidean geometry.
I like finding mysteries, and the other day I came across a perfect one. 2,000-year-old mathematical problem, a statement in a very important book called The Elements, which cannot be proven. I saw a very interesting lecture by Raymond Floods, very, very interesting and very insightful. But when I got about halfway through, I realized what the problem was. 1, 2, 3, 4, 5, 10, 9, 8, 7, 6. 6 plus 5. How many fingers do I have? This is reductionism versus holism. We are outsiders looking in while they were insiders looking out. I will let Professor Floods give you an introduction to the problem and tell you some of the historic context so you can understand what it's all about.
Around 300 BC, with the rise to power of Ptolemy I, mathematical activity moved to the Egyptian part of the Greek Empire. In Alexandria, Ptolemy founded a university that became the intellectual center for Greek scholarship for over 800 years. He also started its famous library, which eventually held over 500,000 manuscripts before being destroyed by fire. Alexandria's Pharos lighthouse was one of the 7 wonders of the ancient world. The first important mathematician associated with Alexandria was Euclid, about 300 BC, who's credited with writing on geometry, optics and astronomy. But he's mainly remembered for one work, The Elements, the most influential and widely read mathematical book of all time. It was in use for more than 2,000 years, and apart from the Bible, may even be the most printed book ever. Euclid's Elements is a model of deductive reasoning. It's a compilation of known results organized in a logical order. Starting from initial axioms and postulates, it uses rules of induction to derive each new proposition in a systematic way. It was not the earliest such work, but was the most important, which is why it survived. What we'll see is that Euclid set out some underlying premises or postulates or axioms. I'll use those words interchangeably. They mean assumptions that he makes, which he doesn't prove, he just sets out. And he uses them to prove his propositions or his theorems. Now, most of these underlying axioms or postulates or premises were thought obvious, and I'll show them to you, except one. This is because many thought that the parallel postulate should be able to be derived from the other premises, axioms, or postulates. In other words, that it was really a theorem, masquerading as a postulate. What we'll do is we'll follow some of the attempts over the centuries to prove the parallel postulate until, in the 19th century, 2 mathematicians, Janos Bolyai and Nikolai Lobachevsky, showed independently that the parallel postulate did not follow from the other assumptions, and that there was a geometry in which all of Euclid's assumptions, apart from the parallel postulate, were true. In this geometry, called, not surprisingly, non-Euclidean geometry, the parallel postulate is false. First of all, we'll look at what he calls the common notions. And all is fine here. They're general truths or assumptions that could be applied to many areas of investigation, not just geometry. Things which are equal to the same thing are also equal to one another. If equals are added to equals, the wholes are equals. If equals be subtracted from equals, the remainders are equal. Things which coincide with one another are equal to one another, and the whole is greater than the part.
As above, so below. This is referring directly to the Hermetic principles.
Very straightforward and very convincing. He's taking those as underlying logical premises. Whereas the postulates have geometrical subject matter. 5 postulates. The first one, to draw a straight line from any point to any point. Good. To produce a finite straight line continuously in a straight line. He's saying that one can do this. To describe a circle with any center and distance. 4, that all right angles are equal to one another. And now for something completely different. Don't worry about postulate 5 yet. It's harder to work out what it is saying than for any other postulate or common notion. We'll come back to it. We can think of the common notions and the postulates as logical and geometrical axioms respectively. Using these axioms and the 23 definitions of Book 1, further definitions were introduced in later books, Euclid proved all his results. Now, let's look briefly at some of the definitions. I'm going to pick out some of the ones, most of the ones in fact, to do with points and straight lines. And you may feel some disappointment now. These are the definitions. We have the postulates, the premises, the axioms. They tell you how to work with things. These are the things with which you're going to work. A point is that which has no part.
A point is the center of a circle.
A line is breadthless length.
A line is a measurement. It is the radius.
The extremities of a line are points.
It's an algorithm. It tells you that you can only draw one radius before you have to draw another circle.
A straight line is a line which lies evenly with the points on itself. A surface is that which has length and breadth only.
Well, I don't know about all of them.
The extremities of a surface are lines. I don't think there's a lot of content in any of them. He doesn't give any definition of a point or line. It's in the common notions and the postulates that he tells us how to work with them and gives their properties and gives their interrelationships.
This is directly connected to the 7 principles of Hermetic teachings. I'm not really sure about how, but I'm sure that if somebody else looks into this, you will find a deeper meaning here. But anyway, the first sentence says, a point is that which has no part. And to me that is really simple. A point is the center of a circle. Next statement says, a line is a breathless length. To me, that means that a line is a measurement. It is the radius. I just do like this. Then you create a new circle here. Just like that. Next sentence tells us that the extremities of lines are points. This is the extremity of lines. This is, and this is, and this is. And all these are points. So I can create spheres here again. I'm pretty sure you can find much more deeper meaning with this, but this is just an introduction to how you can understand this. If you let the algorithm run and just keep reproducing new spheres at all possible points, you will get a known image. And this is what the algorithm tells you when it says that the extremities of lines are points. You can move one radius, but then you have to create another circle. And in this way, you will create this pattern.
Most of the other definitions do in fact define something. They have some content. For example, let me pick out another 2 to do with lines. When a straight line set up on a straight line makes the adjacent angles equal to one another. So there's a straight line, the vertical one, set up upon a straight line, the horizontal one. And when the adjacent angles, those angles are equal, when they're equal, each of the equal angles is right, called a right angle, and the straight line standing in the other is called a perpendicular to that in which it stands. And then 23, now this is important. Parallel straight lines are straight lines which, being in the same plane and being produced indefinitely in both directions, do not meet one another in either direction. And I do want you to remember, I'll be reminding you probably every 2 minutes, but parallel lines, the definition of parallel lines is that they're lines that don't meet. They're not, for reasons we will see, you're not to think of them as lines like so, which is probably how you're thinking of parallel lines. Right? That's a consequence, in fact, of the fifth postulate. The definition of parallel lines is that they're lines that will not meet, and this will be crucial when we come to look at other geometries. Well, Euclid showed remarkable insight and ability in selecting his common notions and postulates, so that everything was deducible from them. But one of them stands out as perhaps seemingly different in nature to the others, and that's postulate 5. So now is the time to look at postulate 5. So let's look at it, and look at it with the diagram underneath, because that will help considerably. If a straight line falling on two straight lines, so the straight line is going to be down here, which I've labelled N. That's the straight line N, which is falling on the straight lines L and M. If a straight line falling on two straight lines makes the interior angles on the same side, the interior angles, there's one which is alpha, another one which is beta. If it makes the interior angles on the same side less than two right angles, alpha plus beta is less than 180, the two lines L and M, if produced indefinitely, meet on that side on which are the angles less than the two right angles. But there's an equivalent formulation of it called the parallel postulate, which is more immediate. And one can show that this postulate 5 is equivalent to this statement, which I think is more intuitive. That if you take a line, there's a line L, you take a point on the line, there's a point P, then the parallel postulate says that through the point P, there's only one, there's a unique line which is parallel to L. In other words, there's a unique line which does not meet L. And I think that's easier to get hold of, sometimes called the uniqueness of parallel postulates.
I feel maybe it's time for some more entertaining stuff, so let me draw a pretty picture for you. See, because sometimes people forget when they talk about math that stuff actually represents something out in reality. So it can get a bit confusing sometimes. So try to imagine this picture.
So once you unpack it, with our intuition of what Euclidean space is, it seems reasonable, but it does seem, as everybody felt from the very start, that it should be something you should be able to deduce as a theorem in the geometry. It's got the feel of being a proposition or a theorem that can be deduced.
Yep, it surely does.
And that was tried for centuries. But they were in vain, because in the 19th century it was shown that Euclid had been right all along. This cannot be deduced as a theorem from the other postulates and common notions.
Really? For centuries? Let me show you how I would do it.
To draw a straight line from any point to any point. Good. To produce a finite straight line continuously in a straight line. He's saying that one can do this. To describe a circle with any center and distance. 4, that all right angles are equal to one another.
Did you guess it? Here's another clue.
The equidistant curve to a straight line is itself straight.
This is where that inside-out holistic approach becomes really important.
Through a point not on the line, there's a unique parallel. The definition of parallel lines is that they're lines that don't meet. You're not to think of them as lines like so, which is probably how you're thinking of parallel lines. Right? That's a consequence, in fact, of the fifth postulate.
I'm kind of wondering how you see dimensions, Professor. This is really simple. It's 3D mathematics viewed on a two-dimensional piece of paper from a three-dimensional perspective. It is not that complicated.